large package like GAMIT. So the basics of what we're going to talk about is doing what we call velocity solutions. You've already seen the GLOBK command files, and you hopefully remember that the way we estimated positions was just by having this command that tells us that the a priori uncertainty in the northeast up components of the sites is a certain amount, and the last 3 columns is for the velocity signals. So the solution we ran yesterday, those files have in them a line that starts with VEL, capital VEL. And those, we're going to invoke that by putting capital VEL at the end of a GLOBK run string. We did GeoRed. We're going to replace the GeoRed with GLOBK, and then we're going to put VEL at the end, and the velocity solution will run. And the big change that happens is simply to say that the velocities are uncertain, and that will tell GLOBK to estimate them. Now, if we do that on that little 1 month's worth of data, you might find, you think, well, month you're not going to do very well, and that's exactly what would happen. We can do that velocity solution, but the uncertainties would be still very large because you don't get much change over a 3-month period. So we'll look at setting up the solutions to do this. When you get into detail with this, when you have a large amount of data, these solutions can take quite a long time. So we'll look at some of the strategies for speeding up solutions. We won't spend too much time on that because you're going to have 20 years worth of data with 500 station networks to be able to do it. But again, there is this 500 station network plan for India. As you all graduate and go on to do great things, you may well end up in a few years from now needing to take 3 or 4 years worth of that data and do this type of analysis. So hopefully you remember these slides back then and you can come back. At the moment, they won't be particularly relevant to what we're doing. And we'll look at methods for cleaning up potential problems. And then we'll look at the way you do different reference frame realizations, just some of the ideas that are there. And we'll give some examples. And again, this whole class of solution involves making decisions about how you want to treat the data, what problem you are trying to solve. And so there's lots of decisions. We'll start this afternoon's practical with a very simple question of how do we actually want to lay out the directories for what we're going to do? What's going to be our strategy to make life easy for ourselves in sort of doing these analyses? So again, the GLOBK solutions is to combine many years of data typically. And during that, you're going to estimate positions, velocities. But in any real data, and as we'll see in our data, you're going to have to estimate offsets because of potential changes in the system. There is potentially to have post-seismic deformation going on as well. And I must admit, some of these solutions, it's not uncommon to get into the range of 10,000 parameters that you're manipulating as we go across. So the requirements for these solutions is an a priori coordinate file with velocity, a priori coordinates and velocity. And that's used to check the daily positions as they come in. We saw that there's a command called maxchi, and that allows you to control that number. But one of the things that's, when you're doing these velocity solutions in particular, is since they often take a long time, you do not want the solution to have some bad data that gets in and then corrupts the solution, and then it sits there putting all this other data into a solution which is not going to be good when it's finished anyway. So we have editing conditions in there to check and try to eliminate anything bad that's happening. So you need that to make sure you've got good quality positions. The earthquake file, we haven't looked at this in detail yet, but we're going to create one this afternoon. If it's a true earthquake, we have a shell script, which I think on Friday morning's lecture we'll briefly just talk about, called SHmakeEQDef. We recommend that's what you use if you think you've been affected by an earthquake, because it will set up the earthquake file for you, and it will tell you whether you were actually affected by that earthquake and whether you need to worry about it. And it actually reads a seismic catalog. You just basically give it a time range, give it a minimum magnitude. Actually, normally all you do is give it a time range, this year to this year, and then a file which contains lat long and names of sites. And then it will do everything for you. It goes off to the NEIDC database to get the earthquake information, and based on the magnitudes there, it makes an approximate calculation of what we expect to happen. So you have that. The other thing you typically need is a process noise model for each station. And again, when you're exploring this, and we might, it won't make a big deal of effect in what we're doing because we have a relatively small amount of data. So we have basically 5 years worth of data. For the other years, we have 2 segments each year. And so we're going to estimate velocities through that. And in some sense, it's not that much data. But if you have every day of the year for 3 years, because of that temporal correlation that's in that GPS data, and we already saw that yesterday in our repeatability plots, right? And when we looked at the time series, those time series dots were not Gaussian white noise values. I hope everyone sort of can recognize what Gaussian white noise sort of looks like. And those were not Gaussian white noise. They were quite systematic. And because of that correlation, if you assume they are white noise, you end up with very, very optimistic uncertainty estimates for the velocities. And I must admit, it's not uncommon under those assumptions. You would get down to 2 to 3 microns per year. It is very common if you just assume white noise for large data sets. So, and we know that's unrealistic because we know if we split the data set in half and do 2 velocity estimates, we'd end up getting estimates which differ considerably from their segments. And again, that's as you go through this and sort of work with data, that's what you test to do. Start dividing your data and see how your conclusions depend on which blocks of data that you use. So the other thing we need is then what we call the process noise parameters for each station. And we will play with this just to see what its impact is. We don't really have enough data to do it the standard way we want to do it. But we have this shell script called SHgenstats, which is generate statistics. And you basically give it the repeatability, you give it information from a repeatability run, the time series, and then it will calculate the process noise models based on the actual time series. It will also give you a recommendation and a file for the stabilization sites that you might want to use in your velocity solution. And so it creates a couple of different files that, again, you can directly use in your GLOBK command file. So when these, as I said, you typically want to set these up carefully. Again, when we have a lot of data, because they do take a fair time to work. So, and again, incorrect solutions don't help you very much if you've done lots of them. If something goes wrong in the middle of the solution, you look at the end, it's not obvious what went wrong and how to fix it. So you want to sort of step this incrementally. So the general strategy we use, and again, this is targeted at relatively large solutions, is you define sort of a core set of sites, 20 to 200 sites, depending on how big your whole network is. So if you are only processing 100 stations, you may, actually at 100 stations, you might not even worry about doing this. If you're doing 500, then you'd probably want to think about doing this. So you might select your best group of stations that you think of. The way you decide that is you've already done some sort of repeatability results. You've already seen, we did actually quite well just by taking the ITRF 2008 coordinate system stuff already supplied to us and using that to generate time series. We were getting 1 millimeter scatters, and it looked actually quite good. So you can imagine if you could have had 200 local little stations in that solution and used that same basic set of IGS stations, all of those 200 stations would have potentially generated the same quality of results if they were of the same quality as your KT case. We need to give a dual name to that station. So actually what we'll do is when we rename it, we'll rename it the other way so I know I get it right at least once. But you could, and it would have generated that result. And so you would take that group of, that set of time series you've generated, and you could select, based on the RMS scatter, the best 20 or 30 of them, or the best 100. And you run the solution with that because it runs very fast when it's that small numbers of stations. And then from that, you can generate the time series for all of your stations again. And then you can do the tests on whether you've got discontinuities, the RMS scatters, the SHgenstats, and you can then add more stations in. And then to repeat that system as you go around. And so eventually you get up to using all of your stations in the solution itself. And again, the aim here is to make sure that large solution is run. And again, the big ones that we run, they take several days of CPU time to run. I must admit, something like 100 odd stations for 20 years only actually takes about 3 or 4 hours, less than 3 or 4 hours. But as the runtime in GLOBK is going to go as the cube of the number of stations that you use and the number of data points that you use as you go through it. Okay, so general methods for increasing the speed in these things which allow for general parallel runs. So you can pre-combine the daily solutions into weekly or monthly solutions. That's a very common technique people use. Actually, from a numerical rounding error point of view, that's actually a good strategy. If you think about one thing we didn't talk about in the way Kalman filters work, but the way they basically work is you start with an a priori covariance matrix, and then every data point you bring in decrements that matrix. And the process noise makes it bigger, but typically the process noise is small compared to our data. So you keep decrementing it. So you might start with 10 meters, and it's in a variance space, and you decrement it down to a millimeter squared or something like that. So that whole summing and decrementing like that is prone to accumulated rounding error. And so one way you solve accumulated rounding error is you sum things in small segments first, and then you sum the segments together, or difference the segments. And that's the strategy. So you basically might do weekly solutions. This is, again, very common when we do campaign surveys. So you might have a 2-week survey, and you would combine all the data from the 2-week survey into one H file that goes in. And then maybe if you're doing this, and that's the only thing you're interested in, you may only do that twice per year. And so you only have a few of them that you need to add together. It runs much faster, and again, because you've got fewer files, the Kalman filter does run linearly with the amount of files you put in. So you can speed it up that way. And again, the numerical rounding error is much better than that. There is one of the options, if you look down in GLLog's help on the output options, there's one called mid-p, which is actually an option to output the time tag at the middle of one of these. If you do a monthly solution, you can have the time tag associated with the middle of the month. By default, because a Kalman filter is a sequential filter that runs forward in time, the time tag by default is actually at the end of the month. So you can make it look, so you can structure it up at the middle. And again, the random walk processes can be applied to those monthlies correctly. And if you're doing post-seismic deformation, you do need to be careful with this. So this is one strategy. Another strategy, which again, if you get lots of data, works extremely well, is simple decimation of the solution. So instead of running every day of the week, just run 1 day per week. And there's actually a command in GLOBK that allows you to do that. And it's, again, one of those commands which is at the top of the file. And you look in the help, it'll tell you it has to do with a decimation factor. So basically it says a decimation factor, and then where you want to start the decimation from. So the default is to start from the first point. And then if you're saying decimation of 7, it would take the first point, then the 8th point, then the 15th point. But you can start, say, from the 3rd, and we do the 3rd, the 10th. And actually, you could then run, in parallel, 7 runs in which the starting day is offset by 1, and then you could compare the results you get from each of those 7 days of the week, where you only choose 1 day per week. And when we've done that, what you find is the solutions are almost absolutely identical. And again, that's a reflection of the correlated noise effect, that using 1 day per week actually is just as good as using the whole week of data. And with the process noise models, it turns out the sigmas are very similar, because once you've stacked a reasonable amount of data, the ultimate velocity uncertainty depends not on the raw data itself, but on the impact of that process noise model. Again, for most sites which have standard levels of it. The final one you have is a subnetting approach. And this is what we actually use to do the plate boundary observatory solution. So it is a solution which has almost 5,000 stations in it. And even with time decimation and anything else, it still would take a very, very long time to run. So what we do is we actually subnet. So we subnet in GAMIT to handle big networks. Now we subnet in GLOBK to handle massive networks. And so that runs very fast. We divide PBO into approximately 8, I forget how many it is, about 70 subnetworks. And again, that's done automatically. There's a program called NetCell. And one of the options in NetCell, normally we use it to subdivide for GAMIT runs, but there's an option to subdivide for the GLOBK runs. and that will be, that is explained in the help to that program. Okay, so before your velocity runs, you want to have a look at what you want to do. Surveys need to be combined into one solution per survey as typical. And then once you've done that, you can just run GeoRed with the combined solution as you go across. We saw SHplot pos yesterday, and that's a very, very powerful tool. It does much of what you wanted to do, as we saw. And so we'll use that again this afternoon in the tutorial sessions. You can also do it by hand. There's this program TS-sum, which we looked at, which you give it a directory where you put things. And then there's what we call product ID. That's sort of very PBO focused, but it's useful because it allows you to identify an institution. Very useful if you're working with other groups. Some character code, which normally one refers to the orbit nature, but you can give it anything you like. We gave it first. And then if we're going to do a second run, we would call it second. You know, it's whatever 5 characters spells second. And then you can give it a reference frame. And as we'll see this afternoon, we'll play around with the reference frame. And you can also tell it, you know, to either replace existing series. It by default appends to them. And then you give it a series of org files, and it generates these pos files that can be put in that. And then in the SHplot pos, you can actually just either specify the org files themselves, or you can specify the pos files. This -k option keeps the pos files when they're generated. There's a couple of other options in there we'll explore around with tomorrow. And this just gives you an example, you know, of a reasonably good repeatability. This is multiple years. So these are actually campaign measurements where this is actually representative of a couple of weeks worth of data all combined together. And so this first one, the scales here are -6 to +6 millimeters. And the time scale, it goes from 2007 out to 2014. These are all very good. And then the little statistics get printed up here with the velocities, etc. And then this is good. And then this is a case which is okay in the horizontals. Again, the scales here are a few 6 millimeters or so. RMS scatter is there's less than a millimeter. It's 2 millimeters in east, which is a bit noisy for that station. But in vertical, we have this big outline. So if we ignored that in doing a velocity solution, you can see by eye that the velocity estimate would show this very large rapid subsidence. So you want to take that into account. And we saw yesterday that one of the ways you can take that into account is with this sig NEU command, sig northeast up. And you would just add sigma to the nice thing about sig northeast up is it's the sigma in north, east, and up. So this point looks good in north and east, so you didn't need to add any noise for that. But in the vertical, it's off by 50 millimeters or so. So you might add 100 millimeters of noise. And so if I put a 100 millimeter error bar on this thing, it's not going to affect that slope. And I will get what probably is actually a subsidence rate for that site quickly at it. So that's one approach. If it was really disastrous, I could also put a rename into the EQ file, and you rename the site to end in XCL, _XCL, and that would get rid of it. And so that's sort of the 2 standard ways we do it. If in general this was just sort of looked, you know, had a lot of scatter relative to its error bar size, we could also just give it large process noise to account for all that extra scatter as we go across. So excluding outliers and segments of data, as I said, you can rename them out with the XPS or the XCL commands in the EQ file. When this command has various options to it, the help explains that, but in particular you can specify a time range over which this can be done, which is common to get rid of a block of data. You can have it start at a certain time and then just everything after that time is excluded. You can also give it a very early date and then an end date, and everything up until that date would be that. And you can also optionally put in here, you know, certain H files or certain strings that appear in the H files to have it excluded from only X thing else. So the XPS is an option which does not exclude it from a GeoRed run, but it does exclude it from any velocity solutions. So in the time series with the XPSs, you can still see them. The XCL gets rid of them completely. And so that would take them out of the time series, which if you're doing statistics is what you'd want to do. Okay, so to run GLOBK, again, you create a new GDL file. So had we done combinations, I must admit, our naming convention when we combine things together is to end the name with a capital GLX as opposed to a lowercase GLX, just to keep it separate that this is a combined. And then you would output again into some GDL file that you run. GLList is a program which allows you to see what's in. We haven't played with that yet, but you'd give it this. The simplest use of this is just GLList and then the name of a GDL file. And it will just list the contents of everything that's in that file, how many times sites get used, when they start, when they stop. You can also give it earthquake files and other information which will allow you to actually edit that data in the way it would be edited in GLOBK as you go across. So then you run GLOBK, and this may or may not take some time with, say, the velocity estimate in. Use tsfit to check it. And sometimes it has to be, so again, just you would use that. There's a way to make sure your a priori coordinates are consistent using this program called Unify APR. We don't normally need to do that too much as we go across. So now to run GLLog for different reference frames. So when you run GLOBK, as we saw yesterday, we can put in that org command, org_command to have it run automatically. But once we've done that, provided we don't delete the scratch files, which is what you'll see, it's not deleted when we run the VEL solutions, we are left with the commands that allow us to run GLLog by itself. And again, that's much faster than restacking everything. It just takes the full covariance matrix. So you could run GLOBK, under this is just a GLOBK vel, and then once you've done that, you could run GLLog and then say a North America fixed, where you would give it a command file here which uses the North America fixed reference frame rather than this no-net reference frame. And again, things have to be loose when you do that. So to have that, you make sure you put the com file splat.com command in, and then do not use delete scratch yes in GLOBK. This delete scratch, if you don't have that command at all, it won't delete the files. So it's only when you put that card in explicitly that you want to make sure you don't. The APR north must be loosely constrained, and then APR rot and APR tran may also be needed, should be used actually if you've run the standard baseline solutions to make sure that the frame can actually rotate and translate. So use of equates. So when you have earthquakes or renames, the way it's handled in GLOBK is it generates a brand new station name, has the same first 4 characters as your station, underscore, and then something at the end of it which differentiates it from the other sites that are out there. So it's treated like a completely separate site. So when you estimate velocities and positions, you get a position and a velocity separate for these sites. So in general, if it's been equipment changes, there's no reason to think that the velocity is different before you changed it to after it's changed. So what you want to do is you want to equate the velocities before and after the earthquake happened. And so there's several commands in GLLog that allow you to do that. And the general command is called equate. And it allows velocities to be specified. It's generally, you can use it for actually specific pairs of parameters if you wish to. Generally, we use it in a version which is called equate dist, which basically allows sites separated by less than a specified distance to be equated. So if it's been an antenna change rename, the antennas are within a few millimeters of each other. So you might have this equate dist as down at 1 meter, every site within a meter. But also when you're doing survey mode, it's not uncommon over many years for you to have had to move a site by a little bit. And in fact, your particular site we're processing, that's exactly what happened. It's moved by about 10 meters. Well, over 10 meters, I expect that to have the same velocity as before. So we'd have an equate dist of 20 meters, and so it would match. It'll go across, and then you give it the things you want to equate, and typically that would be something like the north velocity, which we call north dot, E dot, N dot, and U dot, for example. And that's what you tell it. So you give it equate dist, and then the thing you want to equate over that distance. We also have one which is equate for char, which equates on sites which have the same beginning 4-character code. That's really useful because sometimes you do have sites close to each other, but you actually don't, they are separately sites, and for various reasons you don't want to actually equate their velocities. You want to be able to see how different the velocity is between these co-located sites. And so this way you can actually tell it to just equate those things which have the same first 4-character on them as you go across. When you do this, there is a chi-squared increment. The equates get printed out one by one, as we'll see. And there's a chi-squared increment that tells you, when I make this equate, what is my increment in chi-squared? I would hope that increment is going to be 1 or less. And if it's 2,000, then you think, well, something's inconsistent in that equate. And so there is an unequate command that allows you to specify specific things that should be unequated as you go across. Now, when you're using all of these equate systems, the philosophy in GLOBK is you're actually equating the adjustment to the a priori. So if you're thinking about a velocity, it's the adjustment to the a priori velocity on the site that you're going to equate. When the rename happens inside of GLOBK, then it will carry the velocity information from the earlier site to the new one automatically, and so you don't have a problem. But in many cases, the name may have already appeared someplace else, and you might end up actually having different velocities on these two sites. So whenever you do the equates, you always should add the fix a option to the org outs, and that means fix a priori. This works 99% of the time. We have had cases of very complicated renaming sequences where it can't quite work out who should have the same velocity. But generally this works well. The best strategy is to have an a priori coordinate file in which they are the same, but this is a relatively fixed quick that's reasonably robust. But whenever you use this option, you should just check that those things that you equated, you get a summary of the velocity field, that the velocities in fact are equal to each other, and you'll always see that the adjustments are equal to each other. You should check that the velocities themselves are equal to each other when you do it. So the other thing is the use of the SHgen stats, for example. And again, these velocity solutions are typically very iterative. You do them many times to refine in precisely what you're doing. So you generate your time series in IGB08, which is exactly what we did. You would fit the time series with TS fits, find any outliers, nature of the equates. One of the options in TS fit is to discard data which are more than an n sigma specified off. And so you can actually have it, and it will generate an earthquake file, which actually has those renames in it. So GLOBK will automatically delete. It generates the XPS or the XCL lines for you as you go through the solution. And you might have the nature of the log. So when you look at the time series, for earthquakes that are generally earthquakes which are larger than, say, magnitude 7.5 up into the 8s, we typically these days see post-seismic deformation after the earthquake. And so one of the things you can do in TS fit is to actually play around and see whether you want to fit that with an exponential or with a log. If you output the a priori coordinate file from TS fit, all that information actually is fed into GLOBK through what are called the extended parameterizations of coordinates as you go across. And this allows you to generate this self-consistent a priori file. This is the way we recommend you do this at the moment. You use it with the realistic sigma, or what we actually often call the FogMex model now, to get the process noise. If you have really dense networks, and you want, so in something like PBO, there are certain areas which are extremely dense with stations, Southern California along the San Andreas Fault. And so, and those stations also tend to be very well behaved because they're in desert environments. So the standard SHgen stats, 90% of the stations in that region all come up with really good looking statistics, would all be really good reference frame stations. The whole of PBO is about 2,000 stations, and we probably have 700 of them, maybe even more, maybe 1,000 of them. Half those stations are in this very narrow band in California. So if we just did the stabilization selection based on the good sites, we would have it dominated by this little strip in California. And that would work really well for California, but would look terrible in Alaska, and it would look terrible in Northern America, and it would look terrible, say, in the Caribbean. Lots of stations which tend to be a little noisier. Again, Caribbean is equatorial, and again, that we see more scatter in equatorial stations. So there's what's called STAB-RAD, which stands for stabilization radius, allows you to specify this. It'll generate this hierarchical list of stations for you. So it will take, typically we do this over maybe a few 100-kilometer scale. So there's essentially one point every 300 kilometers across your whole network, and then at each one of those points there's a list of preferred stations. So you don't get this overweighting towards the really good parts of your network when you do that. So you run that, you run your GLOBK solution, you extract from the GLOBK solution the a priori coordinates, which you can do with a shell script, and then instead of using IGB08 now as your a priori, you use your own estimate of the a priori. Regenerate your time series using your best choice of reference frame stations now for the stations you have. Go through this again and try it again. And this way you can sort of hone in on a system which is very good for your own results. So to get out that, the way you do those comparisons, we have a shell script called SHEXGLOBK. It's extract GLOBK. You give it your org file. It has some options. The ones we're going to use this afternoon is this -vel, which is going to extract the velocity estimates from there. This -rmdup just removes any duplicate lines, because when you do these renames and equates, you end up with maybe 3 or 4 station names at the same physical location. If you've done the equates, they all have the same velocity. And so the rmdup basically looks at that, and if they are the same, doesn't put them in the file. If there is a difference from somebody, it'll actually show you the one which is different, which is out there. You can also use this program called VELROT, which allows fields to be rotated and compared. Also, if you do 2 different solutions, allows you to compare what happens. So if you wanted to test a strategy, which we'll probably have time. Now, again, there's many things we could do this afternoon, but one of the strategies we could do is, well, what happens if we turn on translation explicitly, which is what we recommend you do? What happens if you don't have it turned on when you do a velocity solution? We can run the 2 velocity solutions very fast, extract the velocities, and then compare them. And VELROT, and when we compare them, we can, this allows you to actually specify reference frame when you do that. You can also compare them absolute, or you can compare them allowing for a rotation and translation between the 2 fields. And so as you go across, and then there's a set of lines, again, this sort of standard way we have things that we can grep on. There's lines which begin with S space at the beginning of the line. So this is a grep, single quote. That actually looks like a back quote the way that's written, but it's just a standard forward quote. Up at close forward quotes, and you would do it on the output of the VELROT, and it would give you the statistics in north, east, up, and the northeast combined. So you can have a horizontal, so you can just have our fit horizontally was this amount, 0.2 millimeters per year. Our fit vertical was 0.6 millimeters per year. So it's an easy way to extract statistics for papers and things like that. So a lot of what we also extract is sort of aimed at writing papers as well, I must admit. So we were talking about the strategies of doing different things. This is an example of, this is 1996 to 2015. So this is basically 20 years worth of data. And in this first solution, we used day 1 of each week. In this one, we used day 3 of each week. And we ran the solutions, and so when we compare them, we did this over a small number of stations. And when we compare them, what we see is the weighted mean. This is in millimeters per year. So the differences between those 2 runs are 0.02 millimeters per year, means 0.03. The RMS is 0.04, 0.16 millimeters per year. But the more important number, as I said, whenever you do comparisons, the thing you compare with is this normalized RMS. That is the chi-squared per degree of that freedom. Now, statistically, actually, these are independent solutions because they do not share data at all. And so when you have a chi-squared statistic of 0.2, or a square root of chi-squared of 0.2, then it says these 2 solutions are highly correlated. even though there is nothing actually in the data that correlates them. That means intrinsically the process, the GPS system itself, the noise characteristics is what's doing that correlation. So we can do that between day 1, we can do it with 1 and 5, and again, whenever we do this, these things always turn around by turn 2. And that's why I said when you have continuous data processing, taking a value once per week essentially gives you an answer which is exactly the same, again, at, well below 1/10 of a millimeter per year, and well below this uncertainty in the statistics. This one, you can hopefully read this in your, you actually have access to the electronic version of this, right? As well as the, yeah. So hopefully you can read this in the electronic. But again, this is comparing doing the solution with the big GLOBK velocity solution, which for this particular solution took over a week to run. Takes about 10 to 12 days to run, with a time series analysis fitting to the time series which have been done in a consistent reference frame to the velocity solution that we ran, and which that time series solution actually wasn't that fast. It took maybe 30 or 40 minutes to run because there was 2,000 odd stations. So this is a comparison now over 2,000 stations. These S lines are the ones that come out of this bell rod. So this is just a comparison of these two velocity fields done in different ways. And again, what you see is that the weighted RMS differences between them, at this stage I can read this, this is 0.12 millimeters per year, 0.3 millimeters per year, and the chi-squared again is around about 1 for this type of solution. And so this is different comparisons between doing the fit with least squares, doing it with a Kalman filter, and comparing it to the big GLOBK solution. So the long and the short of this is that once you actually have the reference frame well defined, then getting velocities from the time series is probably you get basically the same quality of answer as you do from the large GLOBK solution. What the large GLOBK solution allows you to do is to define that reference frame in the first place. And to define that, you don't have to do all of the data you have when you have a very large network. You can do it with a few hundred stations, which is a very fast run. And so that's sort of the take-home message, that if you do large networks, you want to define the reference frame very well and then use the time series. It's a very efficient way to do that processing. You will not have that problem at this point. You need, as I said, to be in the several hundred station range for this to be starting something you worry about in doing these solutions. So just sort of final comments here. Large solutions, decimated data sets, small networks, and again, the runtime is linearly proportional to the number of sessions you use and goes as cubic of the number of stations that you're using in the solution. And make sure when you're doing these velocity solutions that your a priori coordinate files are consistent. So you have multiple names of stations. Make sure they all have the same velocity. The best way to do that is with tsfit and use the out APR file command. And it will generate an APR coordinate file that does that precisely for you as you go through. Okay, we're going to find those velocity solutions this afternoon. As I said, it's really only a few lines difference in the command file. We're going to think about, since we have multiple years, we're going to think about, well, how do I want to set up my directories to do this? Because we want to run multiple years. And then we're also going to think about, well, every one of those years we're processing, we're going to use the same command file. So why should we do it? We made a G solution directory in 2011, but if we're going to run this for every one of those years, do we have that command file in that directory for that year? Or is it better to put it someplace else and just use an indirect path to it, ... and then down to where it is, for example. That's what we're going to actually do, and we'll think about that this afternoon. So now we're going to talk about repeatability. Now this falls back into our error analysis notes, and so we're going to sort of look at some of the things that go wrong to a large degree as we go across. So we've shown some common time series, linear rates. There's also often seasonal terms in there. The correct term is seasonal. We actually fit them with annuals typically, but these things really aren't annual sine and cosine functions. They have an annual period, but their shape can actually vary a little year to year, and their amplitude definitely can vary year to year. So there's a whole field of study of how best to represent these seasonal solutions, and actually from the statistical world. I'm not sure, do you have seasonally adjusted unemployment figures for India? Maybe not. That's the big thing in the US is, the unemployment rate is a certain amount. And they always talk about seasonally adjusted unemployment rate. And what it means is throughout the year, the employment rate actually does have a cycle to it. So in the summers in California, for example, there's a lot of crops and stuff that need to be picked. And so a lot of people get employed. And then in the winters, certain jobs that really require nice sunny weather, even construction workers, right? They tend to take long extended vacations during the winter when they can't work outside. And so the numbers drop down. So seasonal adjusted means that you take that sort of fluctuation in. Anyway, there's a whole statistical development area from unemployment statistics that sort of deals with this. So there's lots of interesting stuff to go out and explore if you want to think about how to handle seasonally adjusted terms. And we've already seen the impacts of correlated noise, right? We had those two solutions that had completely independent data and had a square root of chi-squared of 0.2 between them, which statistically you just has zero probability almost of occurring. So there's also other irregular perturbations that occur due to equipment and environmental changes, earthquakes, nonlinear motions due to earthquakes, and other stuff happening. And then we'll talk a little about recommended. So changes of equipment. Antenna changes are our main concern, although there are cases where changing the receiver, you will see a change in the position. And there is even a documented case of changing an antenna cable and seeing a change in position. And what those actually correspond to, as far as I can tell, is that there is a multipath signal at the site. You change from brand X to brand Y receiver, and the new receiver with later firmware and better stuff has more sensitivity than the old receiver. And so all of a sudden, it starts seeing weak signals in places that the older receiver could not. And because it's in this sort of multipath environment, that systematically shifts the position. The same with the antenna cable. The one that was specifically done was a preamplifier was put into the cable to make it stronger signal. When they did that, they got more data and the position changed. So in those cases, we think the receiver effects are due to the environment in which the antenna is mounted. But antenna changes definitely change. We see many, many cases. Last year, at the end of last year, in the reviews of Geophysics, we have an open access publication. That means all of you can read it. It's about the Plate Boundary Observatory. And we actually give tables for that observatory where we've had thousands of antenna changes, literally. The statistics for each type of antenna, how much on average it changed, and what was the RMS scatter. And in fact, on the PBO FTP site, if you go through that through unavco.org, you can actually get all of the values of all of the antenna change offsets that we have. There's several thousand. We have a file of them. We actually update that one every month as we add new antenna changes to it. So there's a lot of information out there if you want to look at how big that is. So these antenna have phase calibration models, but as far as we can tell, when the antenna is put in a real environment, there's other things that happen. You might have noticed that we were looking at one of the antennas, one of the Trimbles, and it had a 2 millimeter east offset in the phase center model. And that means if you rotated that antenna, then it's going to change its position. 2 millimeters east will go to 2 millimeters north if you change the orientation. And that particular 2 millimeters actually occurred when they put a radome on it. The original antenna doesn't actually have that. It has a much smaller number. So you have to wonder, when you put the radome on, does it matter which direction they put the radome on? So these are the sorts of things that antenna characteristics at this level have. And so our general rule is if you change the antenna, assume the position has changed. And if you're doing surveys, and you want to be very, very careful with the surveys, you should always go back to the same survey point with the same serial number antenna, and you should go back with the same mount. So rather than using, say, a tripod mount where the height changes every time you occupy it, it's better to use what they call a fixed height mount. These pole mounts, which typically have chains on them that allow you to make it go vertical. So that's the recommendation. Keep the serial number the same and keep the pole if you're doing really good survey measurements. Because there's no reason why these effects that we see in continuous stations don't affect survey measurements as well. So we have that. Now, we have, again, we try to supply everything you need. We have a program, actually, called STINF to rename. Station.info to rename. and it automatically creates the rename entries for the site, which will put that in. In fact, even though you've changed by 10 meters in position, because we changed the antenna, we can use this afternoon when we account for the fact that your site's in a different place. And we will find that that Trimble to Leica antenna is a 10-meter effect, which is the biggest effect we've ever seen for an antenna change. But anyway, so that's what we tend to do to get all of these in. So again, this is just an example of a mount on an antenna. This is some of the effects that come from multipath environment changes. So this is a site which actually sits out here on this little rock, and much of the time when this is a survey measurement, much of the time when this is occupied, it has nice grassy fields on it, but there was big Californian wildfires, so that's the rock. That's the rock in there. So this, when it was observed this time, lots of grass around it. When it was observed this time, everything had been burnt down in the Californian fires. And so when that happens, we actually see this change in the position of the station as that goes through. So again, this is this SHTS pos. One of the things you can put in here, you can give that plotting program an earthquake rename file, and it will actually mark when they have. So you can actually see the impacts as you go across. So the renaming scheme that we use for this is our original name start as your 4-character code _GPS. For the first antenna change, it goes to 2PS, then 3PS, etc. And then beyond 9PS, it converts to a letter starting at about JPS. And the reason we start there is that the A, B, C at the beginning, we use to designate antenna changes where we do not know why the position seemed to change. The unknown comment. And sometimes that can be a failed antenna, can be things often, as we said, we don't know exactly why it has. And so they go from 9 to J to K. Fortunately, we have not yet run out of letters. If we do, we're going to make get rid of that station because it's got way too many jumps in it. So the manual renames, as I said, we start with A, B, C, etc. as we go across. So these all end in PS. Now, earthquakes. This is a classic earthquake. Which one is this? 2010. This is the El Maya-Chuchapa earthquake. Mexico. This is up on the just north of the Mexico border. And it shows a couple of important things that happen. You clearly see the discontinuity at the time of the earthquake. But the other important thing that happens is you clearly see that this data after the earthquake doesn't look like the data before the earthquake. Somewhat disappointingly, I suppose also, there's no evidence before the earthquake that anything was going to happen at the day of the earthquake. So that's one of the things people always look at time series, trying to see whether there is some observable precursory signal. And so far in time series, there's nothing definitive that's been displayed. So this is actually, again, one of the really active areas in earthquake research is to understand what is the precursory thing. You've probably heard of foreshocks to earthquakes. Do you know how a foreshock is determined to be a foreshock? It's determined to be a foreshock because the actual earthquake happened. A big earthquake happened, and then everyone goes back and looks, oh, we had all these little earthquakes in that region before the earthquake. Those are the foreshocks. Unfortunately, we do not yet know how to take a series of little earthquakes and realize that they are a foreshock to a big earthquake happening. But what that tells us is we know there is something going on before the earthquake. And we just haven't really worked out what that pattern is. What exactly is it? There's tantalizing hints from different earthquakes, but certainly for large earthquakes, one of the problems is we don't have that many of them. And so, this is one of those that, by the time you get to my age, maybe we will have seen enough of heavily instrumented earthquakes where we've had good monitoring in Japan, in California, Turkey, lots of different places, even in the Himalayas, that we do start realizing what that pattern is. The same way we have for volcanoes. So a monitored volcano typically will not erupt without us knowing it's going to erupt. So I'm always hopeful that just at a much lower level, that we're going to be able to do that eventually for earthquakes. That is still unknown. But anyway, so we have this. So you have to take care of that. One of the things you do worry about with earthquakes is that on the day of the earthquake, even on, you don't see it here because we edited it out, I think. But when you actually have, this is 50 millimeters, so this site displaced by about 60 millimeters in that direction, 30 or 40 millimeters. That goes actually through the processing perfectly well. It does not throw out all that data. And what you end up getting is the position estimate is somewhere between the pre and post-earthquake value, and it depends on the time of the earthquake. And if the earthquake occurs at midnight or midday UTC, in the middle of the day, the point will literally fall halfway between. If it's in the morning, it'll be closer to the Van Ven. If it's in the afternoon, it'll be closer to the one down there. So always be a little careful that you will see an anomalous little point here often, but it's often an artifact of the fact that we actually process data across the earthquake. And when you're being very careful, what you do is you actually use the SES information in SHGAMIT to process up until a few minutes before the earthquake as one session, and then after the earthquake, after maybe 10 minutes to allow for the surface waves to go through after the earthquake. And you get two values on the day of the earthquake, one before and one after. And when you do that, you'll see one's way up here and the other is way down there. So this thing in here, we often found that a logarithmic function represents this quite well with a varying time constant as we go across. So in GLOBK itself, when it estimates, it does the estimation with a logarithmic function. Actually, these days, we prefer to use TS-fit on the time series, and then we can fit a combination of logs and exponential functions as we go across. And then the extended a priori entries allow that information to get into GLOBK. So we also have, as I said, we have this SHmakeEQDef program. And what this little plot shows is as a function of magnitude, the hypercentral distance out at which you expect to see about 1 millimeter's worth of motion based on a whole series of dislocation models for these different size earthquakes. And that's what's shown. And again, because earthquakes are complicated, it's not a simple distance of radius. If it was point source isometric, it would tend to drop as the radius squared. And that's the model we use. But these earthquakes, typically if it's a strike slip, has a cloverleaf sort of shape to it. So some directions, it has a large impact on that, etc. And so what we end up doing is this SHmakeEQDef has an empirical fit to this to just allow you to take the magnitude and come up. And under real earthquake, a really big earthquake, you might actually underestimate it, and there will be some places where you will underestimate it. But it is a good indicator of how to do that, and it also then generates the EQDef lines that you need to do that. One of the things which is in the software as well is a program called Displace, and there's also one called Simplex. Simplex allows you to take a set of coseismic offsets and fit an earthquake rupture model to it, and then Displace allows you to take that earthquake rupture model and to calculate the displacements at different locations. That Displace program will actually generate now EQDef lines for you with the statistics that you need for that particular earthquake that you're actually understanding. Generally, again, when we do this, we find that single fault plane solutions at this level work extremely well. So you take the CMT, the central moment tensor solution. Anyone who's ever done earthquake inversions, these are very highly nonlinear problems. So you have to be a little careful. You just can't sort of blindly do it. You need to keep a little bit of realism to it. And, but you generally find the magnitude is actually well fit with these things. But you can sometimes get strange sizes of the fault plane. You might have a long, thin fault plane, etc. So you've got to keep it realistic. Simplex allows you to specify which parameters to estimate to try to recover the fault plane. And often you find it's best to constrain things like the depth, for example, based on what the seismic catalog said, rather than allowing all the parameters of the fault plane to be free. But anyway, that's part of the, under the Displace directory is where those are located. Those are sort of, those are sort of use at your own risk sort of pieces of software. So nonlinear motions, as I said, there is a logarithmic decay. This sort of people think of this as a fault after slip model. The perturbation in velocity reduces as 1 on the time after the earthquake. It actually doesn't depend explicitly on the time constant of the earthquake. And then you have exponential models. These are typically what people think are associated with viscoelastic relaxation. These decay to a certain value. So the big difference between these two models is that and this is reasonably well highlighted back in this figure, in an exponential decay model, this will exponentially decay over a certain length of time, but then very rapidly you expect it to come back to this velocity. And what you'll notice here is if I take this velocity out here, that velocity doesn't look anything like that velocity. And so this, I can either have multiple time-scale exponentials, which I can do in TSFit. If I'm not mistaken, I think you might have to shift the earthquake origin time by a minute or so to have them be separate. Because if you give them this, yeah, you do need, in the GLOBK thing, you need to have the earthquake origin time be just a little different, or it'll assume it's a replacement estimate or something. But so you can actually fit multiple expansion. But what we find is actually logarithmic curves fit this extremely well. And again, how well they fit will depend on how this behaves as a function of time. So again, with earthquake, there's lots of different things you can do. This is an example for, again, for that station. There's a logarithmic decay for one, an exponential fit for another. And again, you'll know, the conflicts you have here in the east component, which was the one we were sort of looking at, the logarithmic works extremely well. The exponential decay, you can see to fit the tail, you have this rather large excursion here. But then in the north component, it's sort of the other way around. The logarithmic doesn't fit that well necessarily. That doesn't fit that well here. But again, the exponential sort of fits well, except it's still got this rather large systematic. The scales here are about 5 millimeters. So it's a reasonable scale. In the vertical, you'll see that there's actually, that's the seasonal signal that we see in many, many things as we go across. And of course, things can get complicated because you have multiple earthquakes. This is, again, that same 2010 earthquake, and then there's a big aftershock later on near this station, and so we get a second earthquake. So you end up having that. So for lots of those nonlinear models, we tend to like to use this extended record, which again, things like TSFit automatically generate for you as you go across. There's sometimes undocumented effects. This is a P49. This is, again, a very large, this is that same large earthquake, big displacement, 150 millimeters. Looks pretty good in the north. In the east, it displaces, and then you just have this very strange behavior in here. And we actually wondered about this for a long time. And what this turned out to be was that when someone serviced this antenna, they actually took the radome off. It's actually a Trimble antenna, which has that sort of flat plastic top on it. They left a large metal washer sitting on top of the antenna, put the radome back on, and so no one could see it. And during the earthquake, it got shaken enough that that washer moved over to the side of the antenna and then created this strange, very near-field multipath signal that persisted here until the engineer came back, a year later, took the radome off and said, oh my gosh, there's this big chunk of metal sitting on top of the antenna. So the unknown, undocumented effects, sometimes we actually do get to go back and really work out what went on, and so it's strange. But again, even on this antenna, even with that effect removed, you'll notice there's strange stuff happening in height. And this thing is not a random sort of noise, so these systematic things are stuff you worry about. So other phenomena that are out there, which I'll just run you through, a sort of class of things that we have. Some of these are often non-tectonic. Some are propagation medium effects due to weather and certain meteorological effects that can set up. Sometimes it's failed equipment. And basically, with continuous data, these things are pretty easily to diagnose. And some of the other facts, the multipath and the signal-to-noise ratio measures are often good diagnostics that something is not working and has changed in the sites. Okay, so this is Bombay Creek in Southern California. This is that Elmaya-Chichapara earthquake again. But the rest of this stuff, we actually believe it's creep on the fault. This is a southern Salton Sea. It's very warm down there. The material's very mushy. So this is sort of just random tectonic stuff that's happening. A very, very strange site. So here you put a really large process noise on it. And in fact, the red lines on here are the uncertainties, the 1 sigma uncertainties in the velocity estimates that we get with this realistic sigma orthognomic algorithm that we talk about as we go across. So it basically says, it gives us a very large uncertainty. So if I'd given a white noise, if I'd just taken the RMS scatter of this, which is, it's not great, it's 9, 10 millimeters, but if I did that, velocity uncertainty would be still very tiny with a 10 millimeters of white noise over this duration of data. There's also episodic events around Yellowstone, and this is just a profile across Yellowstone, just to point out that across the middle of the caldera, we get these large changes in velocity, several millimeters per year across the center of the velocity. And again, we have the error bars here computed with the first order Gauss-Markov process model. And just to give you a sense of what those look like, these are the sites overlaid on top of each other. And again, the scale here is now 50 millimeters and 150 millimeters in vertical. So this is the caldera, and you'll see it's inflating, comes down. Some of the sites come off, and this is one of those sites we actually monitor because this has tended to be sort of permanently inflating. And Yellowstone is a supervolcano. The last time Yellowstone erupted, it had global repercussions for many years after it erupted because of the amount of material thrown up into the atmosphere. The timescales on which that happens is probably every 10 to 20,000 years. Where we are precisely in that sequence is not obvious, but everyone's, again, very concerned about this. But again, you can see these are all sites relatively close to each other, and they're just moving in different ways depending on where you are on the caldera. And then there's sort of annual modulations going on some of the sites. So things can get complicated at certain sites. This is one of the stations up in the Cascadia regions of a subduction zone. And this is an important area. Subduction zones are one of these places where it's been well established now that there is slow transient slip events that happen. And they are associated typically with also a seismic signal called tremor. And they tend to be called ETS, episodic tremor and slip. So there's this seismic tremor, original name came from volcanoes and was reflective of fluids moving in the volcano, basically gurgling sort of sound, which the seismometers would pick up. They wouldn't see them as earthquakes, they'd just see them as increased noise. And that's exactly what this looks like, except that that tremor is occurring down on the subduction zone interface. And this is occurring. Now you might say, oh, that looks like an annual. But if you look at the time scales, it's actually 14 months. In fact, there is a red line in here. That is the annual fit to this time scale. So this thing is actually occurring once every 14 months approximately, not exactly. So, and again, when you look at this in detail, this is actually occurring over about a 2-week period. You can actually see the individual daily dots in between some of these points. And this is a site called SCO2, one of the PBO sites. So this is a really interesting geophysical phenomena, and everyone's trying to work out the relationship between this and actually regular rapid earthquakes. And I'll come back to that a little later. And here's the annual signal down the bottom. So you'll see in height, it actually does have this annual up and down motion. But in this horizontal, this is actually about 14 months apart. So we're going to look at some other examples. If you're interested in sort of the range of things that can go wrong, at UNAVCO, there is this website. It's a Google Doc where we actually document strange things that happen in the PBO data set. And they have reports. You can also go to UNAVCO and you can look at what are called the GAGE, AC Analysis Center Coordinator reports. That's the reports we prepare. We're the Analysis Center Coordinator for GAGE as well. And we talk about anomalies in there and give examples of things. So there's lots of information that are out there. This is an example of a new site that was put in. It was actually put near a seismic vault. And the time series looked good until bang, it started to change. And it has all this strange noise. And when they went back out to the site, what you realize is that this whole little vault thing at the top, the seismic vault, has actually collapsed. And so they dug out a hole to put the seismometer in, and then they put a casing around it, but they just didn't do it well. And it collapsed, and it took out basically the GPS antenna, moved in response to that at the same time. So this is a just really local deformation, literally. This is a case where over 10 meters, the velocity is different because the vault is so close there. This is a case of a landslide. And again, it's sort of coming along, and it's not so much landsliding yet, but it's got this strong oscillation in it, and when you detrend it, and it actually, the site sits here, And this is a scarp that's actually has collapsed in the past, and we think it's in the process of collapsing now as it gets seasonally wet each time as it goes through. This is one of the things we see a lot, which is groundwater withdrawal. So here is our GPS antenna. There's a nice lake over here, which is a proxy measure of the water levels. And so here is our site, again, this is 20 millimeters, this goes down 110. So this is, again, our seasonal signal we see, boom, 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 and then it starts getting bigger and bigger. And then the blue line is actually the lake level that's out here. And so what this is reflecting is that they are pumping groundwater, and as that lake goes down, and it's just collapsing the whole area around here as we go across. And again, that is something we do see a lot in places like India as well, right? There's a reasonable number of areas where the groundwater is being heavily extracted. This is a case of something that's very, very common, which is vegetation growth. And so here we have the time series of the site in east, and you'll see these sort of noisy, jumps up and down, and then it really gets bad, and then it becomes very good again. And the height, we sort of see the annual signal, and then sort of the height seems to go up. Again, this is 30 millimeters, and then this quick jump down. Well, this is sort of the sequence of photographs of what happened. They put the site in, it's on a nice piece of exposed bedrock, little tree sitting over here, but over the next several months, this tree starts growing. And as it grows, it's now obstructing the view of the antenna, making the data noisy because we're getting less data. And also there's a refractive index effector as you propagate through that tree. And then at this point, someone comes out with a chainsaw and reduces the tree from this tree back to this small tree again. And that's the discontinuity. We have a number of sites in California where there's been multiple times the tree has grown, cut down, keeps regrowing. So it's a very common one. This is an example, a couple of examples of bad antennas. And this one actually we were perplexed about for a while because these sites, as you can see, the blue dots are one site. Each color is a different site. And this black dot sequence in here, a place called NDAP, had this large horizontal oscillation in the data. And again, well, that's seasonal signal. It is actually seasonal. And we thought, maybe some groundwater effect going on. But when you look at where that site's physically located, it's nowhere near a water reservoir. There's nothing nearby that would suggest that there should be any groundwater effect at that site. And again, these other ones, the blue ones, they've just got massive signals in them. And so this goes on until an engineer goes out, takes the antenna off, puts a new antenna on, and bang, they all flatten out until the Chuchabar earthquake, which you can see some offsets on these things. So this is a bad antenna does not necessarily mean that your receiver doesn't work. In fact, this class of antenna, these are those Dorn-Margolin choke ring antennas, which are very, very common for high precision geodetic work. You talked about them earlier with suppressing multipath. But the problem with those antennas is that under the little gray radome in the middle, there's actually multiple patch antennas. And what we believe happens here is one of the patches starts failing. And it often becomes temperature sensitive. But because you have 5 patches under here, if you lose one of them completely, you drop your signal to noise ratio by 80%. Drop it by 20%, which is still tons of signal for the receiver to work. But the phase pattern of that antenna completely changes. And so that's what we think happens here. So if you see really weird things, sometimes it's worthwhile just going out and changing the antenna to see what happens. You probably don't have this in this part of the country very much, but you'd certainly have it in the Himalayas, is the effects of snow. And again, one of the ways we can diagnose this and know it's snow is we can actually look at the signal to noise ratio of the antenna. We can also look at sometimes the failures of the antenna after a while. The important point here is that things like snow sitting on the antenna don't just noise it up. They actually can have quite systematic effects, and you can be displaced for quite a long period of time before you pop back as the snow melts off the antenna. So this, again, is one we don't have really a great diagnostic to know for sure. When we have these continuous data sets, it's pretty obvious. But again, even when you want to pick the point at which you'd want to remove data, at the beginnings of these, it's not so obvious. And it is a little strange, right? Because if you think about snow, you think, snow's, big event, and then you might expect to jump, and then as the snow sort of melts off, to come back. But that's not the way a lot of this looks. A lot of this looks like this just growing And is that just a snowstorm every day accumulating more? Having a webcam on some of these sites would be very, very useful as we go through. This is an interesting phenomena that is still under investigation. And it is something you might encounter actually in the Himalayas as well. This set of residuals, if you statistically classified that set of residuals, well, I say what it is, these have a very high skewness to them. So in other words, there's a sign dependence in the noise. It tends to go one way all the time. Not so obvious in the east, but also in the height, you can see that it tends to drop down when it goes east. We're still trying to precisely work out what this is, but we believe it is asymmetries in the atmospheric delay. And we think it might be Lee waves associated with sites, because these sites that tend to show this tend to be in mountainous regions, and the direction of this skewness tends to point upslope. And so Lee waves are pressure waves that form as winds of a certain velocity blow over mountains, and they cause an oscillative signal on the other side of the mountain. The trick is with that they only occur in one direction. When the wind blows the other direction, you don't have them form. And so that's what we think causes the skewness, is it only occurs in one direction of motion of the atmosphere, not the other. And so you don't get the balancing effect that you might expect, say from a land-sea breeze, where in the morning it goes one way and then in the evening it goes the other direction. So that you don't balance it out the way that you might expect. But again, we don't really know that certain. So the recommendations here is know what your goals are in terms of what you're fitting. Sometimes if you have a lot of data, it's just worthwhile throwing stuff away. The only fit for the sort of nuisance terms, it's probably best not to try to fit for everything, because you might remove signal while doing that. And depending on your goal, you can either exclude things, or you can add process noise in GLOBK, or you can use the sig northeast up. That's your sort of three strategies of working out what to do. Sig northeast up to sort of add just variance to an individual measurement, so it doesn't influence the things around it. Get rid of it completely with a rename, or give the whole station process noise to accommodate for the fact that, and it depends a little again on what the nature of that signal looks like as you go across. Okay, so the summary here is, okay, so we started with this basic method of setting up GLOBK solutions. We're going to do that this afternoon in more detail. Looked up strategy for speeding them up, methods of cleaning them up. And this whole repeatability, we looked at different scenarios of what makes things go bad at this level, and some of the reasons we think those happen, and some of them that we just don't really fully understand yet at all. And so the velocity solutions, as I said, that's where you really end up making a lot of decisions about how to treat data, the earthquake files, process noise models, reference frames, which we talked about the other day, where you might do it regionally, you might do it locally, you might do it plate-based, you might do it relative to a no net rotation frame, which is where we started from. So there's lots of decisions you make, and that's the complexity in doing this. Okay, did I? Yep, that's it. Okay, questions? Yeah.
Since that in GLOBK, if we have large data for large networks or say very long periods, we can combine daily solutions into weekly solutions and then into monthly solutions.
Right.
And the daily solutions are weekly solutions are as good as daily solutions.
Oh, they're better. They should be theoretically better because they're the average of the 7 days.
So you said that, or we can combine all the H files. For example, in our case, we have generated H file for each day.
Right.
And then you said we can combine all the data into a single H file. So how do we do that? Do we do that in GAMIT or in GLOBK?
Oh, running GLOBK, the combination is when you run GLOBK, there's a command called out_GLB. And generally, we do that as something like out_GLB, and then some name, often it would just be splat, capital GLX.
Okay.
And that, if I do it that way, then it will take whatever the name of the GDL file was and use that as the beginning of that name. There is another, that's the standard way that we would do that. You can do it that way, or provided you haven't used the delete scratch command and you've named the com file, if you decide, and this is often what we do with GLLog. If you decide, okay, this is the run where it's really good, you can actually explicitly run GLSave as an external program. And you just give it the COM file name and then the name of the file that you want to save. We often, when we do this in scripting, we often do it that way rather than internally in GLOBK.
So then it generates a single H file for all the months.
All the data you combined.
Okay.
And if we run GLOBK, so we ran GLOBK on each of the days of our 30 days.
Yes, sir.
If instead of saying GLOBK, we said, instead of saying GeoRed, we said GLOBK, it would combine all 30 days together.
Oh.
And then if we wrote it out, we would have a H file, which is the average of that 30 days.
And also, while you were talking about changing the reference frame, for example, we have done for our case we have chosen IGB08.
Right.
And then you said later on in GLOBK, we will convert that into a local system for India.
Right.
Just to understand the velocity vectors more conveniently.
Right.
So my question is that while we are changing reference frame, there is that factor regarding the overall conversion rate or the efficiency of conversion. For example, if we are converting from one reference frame to another, what is the efficiency? There is some efficiency. For example, the coordinates and the velocity vectors are converted, say 99%, 99.9%. So there will be some discrepancies while we change from one reference frame to another. How do we regard them?
Yeah, normally, if we wanted to move to the Eurasian to the Indian reference frame, we actually have already that IGS08 velocity field that we have.
Okay.
We have that in the Indian reference frame by applying an Euler pole rotation to the original files.
Okay.
Since we've just applied that Euler pole rotation, and the rotation is what GLLog does to do the reference frame, that will happen exactly. There will be no error in doing that. The only thing would, how close you are to India at that point, is how good is that Euler pole a representation of the motion of India.
Sir, when we are going to measure a movement of station GB receivers, then we are going for surface movement or subsurface movement?
It's the it's surface movement basically. It's you put the antenna on a monument. Generally, that monument, even in the deepest of the monuments we do, goes only down about 30 meters or so. And so typically you're always looking at what's happening in the top 30 meters. Generally, if you're for tectonic studies, we desire putting the receivers into bedrock so that you know that the bedrock then is rigidly attached to the material below it. But again, in a region, again, as you go closer into the Himalayas, for example, that may not be the case. Many years ago, I worked in Kyrgyzstan on the other side of the Tibetan plateau, looking at the deformation rates over there. And one of the scary things about the geology in that region was there is very deep cuts incised into the material. And as you drive through these cuts, you can see competent bedrock and then a massive layer of sediments below it, and then more bedrock. And so if the cut wasn't there at the surface, you think you've actually attached to solid bedrock, but in fact there is actually a layer of sediments below you, which, you know, again, might be you moving as a complete compact unit. That's the assumption we end up making. But if there's a lot of, it's a region where there's a lot of groundwater changes, you know, you might actually have deformation going on in those sedimentary layers. So what we are measuring on this is on the surface, and that at some level is always an issue when we start doing interpretation. But for most of what we've done, we believe that that surface measurement is reflective of what's happening down to the next, you know, couple of, you know, for the top couple of kilometers of the Earth at least. But again, when you are in sediments, that's a big problem. And sometimes you just can't avoid sedimentary basins. When we're in the middle of North America, for example, Mississippi and all those regions, there is no bedrock. You go in the sediments, and then you are at the mercy of what those sediments are doing. The sediments can be several kilometers thick, and they often have aquifer layers in them, and they can compact based on the level of water. We clearly see that in the Great Basin in the US, for example. You can see it go up and down, you know, by tens of centimeters as they pump water in and out of the basin. And then on the edges, when they pump water out of the middle, you can actually see the edges of the basin move in and out. That's the seasonal signal. That's what we think is actually driving it.
How do we actually attach the GPS receivers to the bedrocks?
Oh, and when we're deep, we normally, we use these, again, it depends on how it's installed, but we usually use either short drill brace monuments, which are those triangular ones, and those typically go down about 4 or 5 meters into the bedrock. But in some regions, in the Basin and Range province, which was instrumented to study the nuclear waste repository, and they really wanted the most accurate results they could, they went down 30 meters into bedrock when they put those monuments in. And those are extremely stable. That's still, to this day, one of the best set of monuments we have.
So, sir, when we go for plate boundary observations, so PBO,
yeah.
So the station establishment is different compared to the normal crystal movement, or?
It's the highest quality that we can do. So in PBO, it was designed to study the plate boundary. Whenever possible, all of the monumentation is these drilled braced monuments that basically, since they have a tripod shape that goes out and buried in the ground, they are very good laterally. And as far as we can tell from the reviews of geophysics paper analysis we did, those do perform better than any of the other monuments we have. And it was designed to do that. But we also have pillar monuments. Actually, in fact, one of the areas we study is there are some areas where we actually have multiple monuments all within a few meters of each other, of different styles. And I must admit, the pillar monuments are amazing to watch, because when it rains, you can actually see the pillars bend. They don't bend, they tilt. And, but the number, even there, the number is still maybe 1 or 2 millimeters. And so often, these are in sedimentary regions, we can take all 3 monuments, and when we look at the monuments relative to each other, we see these very significant motions of them. But then when you look at them in the context of North American plate, you see this whole basin is doing something really big at that time, and all the monuments are showing the same thing. So, yeah, monumentation you have to be very careful of, and you want to do as best monumentation as you can. You get it secured. The bigger effect, if I had to choose, would be avoiding obstructions to the sky. So if you have a choice between having a good monument in one place but obstructed, because you can drill the holes, for example, versus not such a good monument, which is on bedrock up a hill, for example, but completely in the open where you have to put in a somewhat less impressive monument, I would go for the less impressive monument up the hill without the obstructions. We saw from the examples of vegetation the impact that it can have. You had a question.
Velocity of my local stations with reference to IAC station or Hyderabad station, what I have to do in this GLOBK process?
Well, as I said, when we do the GAMIT processing, we normally include IGS processing stations around it, and that's what he's done. If you want to, from the MIT FTP site at Everest, you can download global solution H files. And when you do that, if you look in the documentation, you basically just add them in your directory list, and they will get merged with your solution. And then you will have a global network. And you can use the IGS 08 or the IGS 14 reference frame stations. All those stations are in there, and so you would get it. And we could potentially try that this afternoon even. And that's, yeah, and so those are our solutions, and that's what we would recommend if you're going to do that. Okay. Good.